27.4 RC circuits. In this lesson, we will explore RC circuits, which are circuits containing a series combination of resistors and capacitors. Our outline includes a qualitative and quantitative analysis of charging a capacitor, defining the time constant tau, and examining the discharging process. We will also look at energy considerations within these circuits to understand how power is distributed between components. This sequence provides a comprehensive view of how current and charge behave over time when a capacitor is introduced into a direct current environment. Up until now, we have focused on direct current or DC circuits containing only resistors, where the current remains constant over time. However, when we include a capacitor in series with a resistor, we create what is known as an RC circuit. In these circuits, the current is always in the same direction, but its magnitude varies over time. Unlike a purely resistive circuit, the presence of the capacitor means the flow of charge is not instantaneous and steady. Instead, it depends on the state of charge on the capacitor plates. To understand the charging process, consider an initially uncharged capacitor in series with a resistor and a battery. When the switch is moved to position A at time 0, charge begins to flow. It is important to note that charges do not jump across the gap between the capacitor plates. Instead, the battery's electric field transfers electrons from one plate to the other through the connecting wires. As the plates accumulate charge, the potential difference across the capacitor increases, which opposes the battery's voltage. Consequently, as the charging progresses, the current in the circuit gradually decreases. We can analyze this quantitatively by applying Kirchhoff's loop rule. Traversing the circuit clockwise, the sum of the potential differences must be 0, giving us the equation epsilon minus Q over C minus IR equals 0. Here, epsilon represents the battery's electromotive force, Q over C is the potential difference across the capacitor, and IR is the potential difference across the resistor. We use lowercase letters Q and I to emphasize that these values change over time. At the exact moment the switch is closed, the charge Q is 0, meaning the initial maximum current is simply the battery voltage divided by the resistance. As the charging process continues, the capacitor eventually reaches its maximum charge, denoted as Q max. At this steady-state condition, the potential difference across the capacitor exactly matches the voltage of the battery, and the current in the circuit ceases, meaning it equals 0. By substituting 0 for current in our loop equation, we find that the maximum charge is equal to the capacitance multiplied by the battery voltage, or Qmax equals C times epsilon. In this state, the battery voltage appears entirely across the capacitor, and the resistor no longer experiences a potential drop. To find how charge changes over time, we substitute the definition of current, I equals dq over dt, into our loop equation. This results in a separable differential equation. By rearranging the terms and integrating from an initial charge of 0 at time 0, we derive the expression for charge as a function of time. Q of t equals Q max times the quantity 1 minus e to the power of negative t over RC. This mathematical relationship shows that the charge does not reach its maximum value instantly. Instead, it approaches Q max asymptotically as time approaches infinity. By differentiating our charge equation with respect to time, we can determine the behavior of the current. The resulting formula is I of t equals epsilon over R times E to the power of negative t over RC. This confirms that the current starts at its maximum value of epsilon over R when the switch is first closed. As time passes, the current decays exponentially towards 0. This exponential decay happens because as the capacitor fills up, it becomes increasingly difficult for the battery to push more charge onto the plates against the growing internal repulsion. A critical parameter in these equations is the product of resistance and capacitance, which we define as the time constant, tau. 1 tau represents the time required for the current to decrease to approximately 36.8% of its initial maximum value. Similarly, in 1 time constant, the charge on the capacitor increases from 0 to about 63.2% of its maximum capacity. Looking at the provided graphs, we can see the reciprocal relationship. As the charge Q rises toward its ceiling of C epsilon, the current I falls toward 0. These curves characterize the predictable lag inherent in RC circuits. Now let us look at discharging. Imagine we have a fully charged capacitor with an initial charge Qi, and we move the switch to position B. This removes the battery from the loop, leaving only the capacitor and the resistor. The loop equation becomes negative Q over C minus IR equals 0. By substituting I equals dQ over dt and rearranging for integration, we find that the charge as a function of time is Q of t equals Qi times e to the power of negative t over RC. In this phase, the stored charge leaves the capacitor plates and flows through the resistor until the potential difference is gone. The current during discharge is found by differentiating the discharge charge equation, resulting in I of t equals negative Qi over RC times e to the power of negative t over RC. The negative sign is important. It indicates that the current is flowing in the opposite direction compared to the charging phase. Just like the charging process, both the charge remaining on the plates and the current flowing through the circuit decay exponentially, governed by the same time constant, tau equals RC. Eventually, the capacitor is fully depleted. Let us apply these concepts to a practical example. We have a circuit with a 12-volt battery, a 5 microfarad capacitor, and an 800,000 ohm resistor. First, we calculate the time constant by multiplying R and C, giving us 4 seconds. The maximum charge is found by multiplying capacitance and voltage, resulting in 60 microcoulombs, while the initial maximum current is 15 microamperes. Using these constants, we can write the specific functions for this circuit. Charge increases according to 60 times 1 minus e to the negative t over 4, and current decays as 15 times e to the negative t over 4. Energy conservation is vital in RC circuits. The total energy supplied by the battery during the charging process is C times epsilon squared. However, the energy stored in the electric field of a fully charged capacitor is only half of that value, or 1/2 C times epsilon squared. The other half of the energy is dissipated by the resistor as internal energy, or heat, during the charging process. When the capacitor later discharges, the energy it stored is also fully transformed into internal energy within the resistor. Mathematically, integrating the power it squared R over infinite time confirms this total energy transfer. To summarize, RC circuits are characterized by charge and current that change over time rather than remaining constant. The rate of these changes is defined by the time constant tau, which is the product of resistance and capacitance. During the charging phase, the charge on the capacitor increases toward its maximum, while the current decays to 0. During discharging, both the charge and the current decay exponentially. Finally, we must remember that energy is conserved. The energy provided by the battery is shared between the storage in the capacitor and dissipation in the resistor. To conclude, let us consider 2 review questions. First, if a capacitor is charging and a time interval of 2 time constants has passed, what percentage of the maximum charge has it reached? You can solve this by evaluating the charging function at t equals 2 tau. Second, if you are discharging a capacitor and you decide to double the resistance in the circuit, how will that affect the time required for the charge to fall to half of its initial value? Think about how the time constant changes and how that shifts the decay curve. This completes our look at RC circuits.